Come back. Radio silent. Hello? Hello again? Am I back? Yes. Yes, question mark. Yeah, that's a good way to put it. Ay. Um, okay. So, lost a little when entering the third bullet point. Yes. Okay. So once you have a model that fits, look at all the estimates and make sure they make sense. So things that can happen. You can end up with negative variances or model implied correlations that go over 1. If any of that happens, you cannot keep your model. You'll have to fix it and figure out what the problem is. That doesn't tend to happen in path models nearly as much as in structural equation models, but it could happen. So last but not least, just because you have good fit doesn't mean you have a good model. One of the most common questions that I get from people who are just learning this. Let's say that you have a model that looks like this. So these are the coefficients. These are the standardized coefficients between my variables. So for instance, x1 is correlated or predicts y1 with the standardized slope of 0.01. x1 predicts y2 with the standardized slope of 0.05, and so forth. This model could fit very, very well and still have none of the paths be significant. Now, how can that be? Because good fit does not mean effect size. What good fit means is that you have your model adequately captures whatever pattern of covariance is in your data. If you have outcomes that are not related, then you can have a perfectly fitting model that captures those perfect non-relationships. So this model over here on the left is testable, is over-identified. If it is, if the only outcomes that are in the model are y1 and y2, then I'm only missing one path right here. If x1 and x2 were also outcomes in the model, part of the likelihood, then I'd be missing their path as well. But I could test this model fit and still have all of my paths be non-significant. So model fit is not what people think it is. If your variables are not related, then that's what the size of the paths is telling you about. But the fact that you have a path, right, it will perfectly capture whatever association is there. Whether it's an association worth capturing is the question. So effect sizes in terms of the size of the standardized paths and the R-square for the variables involved still matter, even if you have good fit. All right, there, that's a good stopping point. Close. There, look at something prettier for a change. How are we doing? Good. Do you want to see an example? Molly, you're making me hungry. It's okay. I'm like, I want a snack. Oh, in that case, you can keep them. I hate goldfish, so I'm not jealous anymore. Yeah, I just they're one of those the yellow like fake cheese flavor. Jeff is having, okay, now you guys are just being mean. Come on. If I tried to eat Triscuits while I'm teaching, I'd be like, that would not go any better. Of course, that may be what I sound like now. Who knows? Um, on, let me open up a web page here real quick. On your web page for the course, I added a link to the top. I want to point out for those of you who are interested in learning M+, I have added this last row I wrote out for the books website a syntax guide about how to use M+. This is sort of like my cheat sheet for what the different commands mean, and I've also linked to their manuals online. M+ is a modeling program that basically does everything. It does every kind of model in the world, and they update it several times a year so that whatever current developments are in statistics are part of it. It is hella expensive. It is about $1,000 for a license, and it's $175 each year to stay with the updates so that you can keep using it. So it is, it should be available to you inside the virtual desktop. Have you guys checked to see if you have it? You do have it? Okay. It's not the most recent version, but it should be fine for what we need it for. Yes, good. The only catch is that I believe that only like 8 people or 10 people, something like that, can be using it at the same time because of the license restrictions that the university has with them. I know. It makes it somewhat painful. So if you're someone who's already using Stata for this last homework, I see no incentive to learn M+, just to be able to do that. I will use it in the fall for structural equation modeling. I'm not sure how much Stata I'll be able to do, but for now, if you want to use Stata still, that is totally fine. So I'll leave it up to you what software package that you want to use, but here's just some extra resources for M+. Let me show you. This is example 4B. So we have the second half of that. So I'm at part 2 of example 4B. This is the one where we had the 3 people from each family, the adult child, a mom, and a dad. And we were predicting how conservative their marital attitudes were about gender roles from their education. So I wanted to show you what the last model that we did in here would look like as a path model, and then show you the process of diagnosing misfit and respecifying the model to fix it. So in terms of data, since Stata already would have your data in memory, you don't have to do anything different to use path modeling in Stata. It's the SEM package within Stata. For the data file that I'm working with, I had missing value codes in it as -999. So to read it into Stata, there is a option here that removes them and switches them back to dots. In your last homework, I'm using this command because each of you is going to have a data file that has missing data codes. So just make sure that you use my starter syntax that kicks those back out. The reason that I am doing that is because what M+ allows in terms of input data is very, very antiquated. So this is what it would look like if you are a Stata user and you want to be able to create a data file that you can use in M+. It only takes text files with a .dat extension or a CSV extension for comma-separated values. So here is an export command in Stata to create the comma-separated values file that you would need for M+. Here is me doing the same thing in SAS, where this is the step at which I added the missing value codes. In M+, technically speaking, you can just have blanks, missing values be dots, just like they would be in your program. But I have had bad luck with that in the past, of it reading in the data incorrectly because it's not parsing decimals the same way. So this may just be superstition, but at this point I always recommend putting in missing values. And so I'm doing that in SAS here with an array statement. So across all the variables that are going to be in my model, if it was missing, it's going to be -999, and then I'm exporting it as a CSV file. So here's the model that we're going to be estimating as a path model. So in Stata and SAS, the format of the data that we're using is the stacked file. where it's one row per outcome per person. So in this case, person is family. That's the sampling unit that we're having multivariate observations on. And so it's like we have a mom row, a kid row, a dad row. For the SEM package in Stata or in M+, we have to go back to the original wide format, where each family has all of their variables on the same row. So do you remember what the data looked like to start with? Do you want to see that again? Would that help? Okay. Like this. So this first data set right here, this is the wide data, where each family has one row, and the variables for the kid, the mom, and the dad are all on that row. That's the data set that we're going to be using to do path modeling on. It's called wide data. That was how it was originally. To be able to trick SAS and Stata mixed into doing multivariate models, I had to stack it so that all the outcomes were in one column, but we're going back to this original multivariate data set to use the path models. Come back. Okay. So here is the model that we had. Same equation, because it is going to be the same model, even though it's using a different type of data structure. We have marital outcomes for the dad, for the kid, and for the mom. On the kid's outcome is an effect of their own gender, only them. On each person's attitudes are predicted by their own education. And then, because is common in these sorts of areas, I also controlled for the effect of dad's education in predicting the kid's outcome and in predicting the mom's outcome. So that was the model that we ended up with. Okay, with me so far? All right. So first up, Stata users. SEM. And note this thing right here. This makes it very tricky to troubleshoot. All of this right here, all of those lines is one command in Stata. They all are the same thing. They all are part of the same statement, so to speak. So that means to have the syntax span multiple lines, you have to use the line continuator. 3 slashes means keep reading, Stata. I'm taking advantage of the fact that keep reading can also be used to drop comments in here so that I can tell you what's happening in each of the lines. But note then after this line right here, it switches to 2 instead of 3. So that is just a comment. That is not a line continuator. So anything after this, the method statement here, these are separate lines, separate commands, not line continuations. So do you see this little symbol right here? The arrow? It's a diagram. It means the exact same thing as the picture. So what this line is referring to is that these are all outcomes of constant. That means these are the intercepts. Next line, I am predicting the kid outcome from the kid's gender and the kid's education. In Stata, you can go either way. You can say predictors and then have an arrow looking thing. So this is actually a less than sign and a minus sign together. You can have it go the other way. Predictors go to outcomes. So you can write whichever way you're thinking about it. The way that I'm writing it is parallel to what's in M+, because M+ does not have that flexibility. So I'm writing it as Y and then arrow going in predictors. just like it would be in any other model where you list the outcome first and then the predictors. The other thing that I'm doing for you is I am writing out every single parameter that I'm asking it to estimate, but in practice, you don't have to type this much. In practice, all of the variables automatically get their own intercept and they automatically get their own residual variance. The only things that you really have to specify are your choices for how the paths go. So those, see here, 3 lines right here describe the slopes that relate the predictors to each outcome. This line that gives you the intercepts is implied. You don't have to type it. Likewise, this line right here, where it says var and then in parentheses with an E, those are residual variances. You don't have to type it. They're automatically included. But this part, you do have to type because these are more relationships. So covariance puts arrows that are two-headed. And the combination of variables there, so I'm asking for 3 covariances. One of the kid's outcome with the mom's outcome, the mom's outcome with the dad's outcome, and the kid's outcome with the dad's outcome. The E dot is necessary to explain to Stata that I know that I'm asking for covariances among the outcome's residuals specifically, rather than just covariances among the variables. So if I had a covariance that was not among an outcome, like among a predictor, it would just be the word itself, not with the E dot. Okay, how are we doing so far? Good. Method MLMV specifies that you want to use full information maximum likelihood rather than the default limited information. And these are our friends LindComs. You already know LindComs, right? You're well acquainted with LindComs, especially after pancakes and crepes. Wasn't that fun? Yeah. Well, these are LindComs, but what these terms in here are, these are Stata's names for your paths. That's where they came from. So underscore B, and then this part right here, it's the outcome comes first and the predictor comes second. And you might be thinking, how on earth did she know what Stata was going to call the paths? I didn't. I asked it to tell me. So this option, coef legend, what it's going to do is spit out your results with the labels attached to them that you can then use to do math on. I'm also asking for the standardized solution. I'm asking for all of the goodness of fit statistics that it can give me, as well as the R square for each variable. And then asking for the residuals. So I'm going to get the model predicted covariance matrix versus the data real covariance matrix, and residuals is going to give me how far off those two are, so I can help diagnose any local misfit. And M indices, this is my voodoo modification indices that it will help me try to diagnose a misfit and add these things to my model. I'm doing this for more demonstration purposes so that you would know how to do it. Okay. So questions on the syntax for Stata SEM so far? Okay, here's what we're going to get. So my unstandardized solution, that's the typical regression solution that you're used to looking at, where everything is in the units of the original variables. So I have added a column out here that tells you what the analog is in mixed for where each of these lines would be found. So for instance, kid marital is the outcome, is being predicted by kid's gender. So that coefficient right there is the same thing as the effect of kid gender on the kid marital outcome in mixed. So each outcome here, like that's one regression model that happened. The constant is the model intercept. I have the effects of kids' gender, kids' education, and dad's education predicting that one outcome. Likewise, I've got the coefficients for mom's outcome predicted by her education and dad's education. And then dad's outcome is actually only predicted by dad's education. That was the model that we had fit before. Down here, the var E, those are my residual variances. So they would have shown up in the R matrix. And down here are my residual covariances that also would have shown up in the R matrix. Okay. So you guys already know how to interpret all this stuff. So let me look at this line right here as an example. It's coefficient, standard error. This is a z, by the way. There's no denominator degrees of freedom. And here's the p-value. So for every year more of dad's education, his marital attitudes go down by 0.05. And that means he becomes less conservative. It's just a slope, same as usual. So you've got 3 slopes here predicting that outcome, 2 slopes here predicting that outcome, and 1 slope predicting the dad outcome. Here are my lincoms. So I'm asking whether or not the size of the effect of dad's education is the same across outcomes. And here is the thing that told me what it was calling each of these parameters. So for instance, this slope right here, that is the effect of gender on kids' attitudes, it is calling that this. So if you want to do linear combinations of parameters to try to get, say, model predicted means or simple slopes or model implied mean differences, any of that kind of stuff, you have to know what Stata is calling those estimated parameters. This table provided by CoF-Legend tells you that mapping. And it's y, x in each of these things. Here's my standardized solution. This is something that you guys have never seen this semester. You would typically only see this in general linear models. These are the standardized slopes. If I had converted all of the variables in the model to z-score versions with mean 0 and variance 1, these are the slopes that I would then get. So this is the standardized solution that allows me to assess the relative comparison of how strong these effects are. So these have been converted onto the same scale. So for instance, if I look at these two numbers right here, it looks like the effect of the kids' education on their outcome is greater than the effect of dad's education. So I can directly compare these because now they're on the same scale. I could do a significance test for that if I felt like it, but this would be the way to make those sorts of judgments. Likewise, standardized covariances are residual correlations that would be in the R-core matrix. Okay, here's my fit statistics. So how many degrees of freedom do I have in my model? What's not there that could have, what could have been? 6. So what am I missing? It's hard to tell without a picture. The pictures really do help. But I can tell you, just based on the equation, what I don't have. What did I leave out? Let me find the model again. Okay. I only have the effect of the adult child's gender on the adult child's attitude. I don't have it on the mom's attitude or the dad's attitude because in part one of this example, we found it to be non-significant, so I took those out. Okay, am I still there? Okay, so there's two. Likewise, we have the effect of dad's attitude on all three outcomes, but we only have the effect of kids' education on their own. So I'm missing kid ed to mom and kid ed to dad. Now, arguably, none of those paths make sense. Like, why would a kid's education affect their parents' attitude? It probably goes the other way. So that's 4. And mom's education is only predicting hers, not the kids or the dad. So that's where we get the 6 from. Now, is it acceptable that I've left those things out? Survey says. So here's the fit statistics. This column actually from Stata was generated by Stata. So what looks like notes, they wrote for you. How nice was that? So like this chi-square right here, that is the likelihood ratio test of your HO model versus the saturated model. So this is my note that I wrote for you. Stata is not going to help you this much. So this is a test of exact fit. Non-significance, that's my p-value, is actually good. Do you remember why? What does a non-significant result here mean in comparing your model to the saturated model? Anyone? I'm eagerly watching the chat window, or you could just unmute yourself and talk to me. It's not worse? Question mark? Correct. Not worse. That means that according to this, on the whole, the model that we fit adequately approximates the patterns of covariance that are in the data, on the whole. 0.09 would make me a little bit squishy. Like I'd want that to be really non-significant before I'd feel good about that. Let's look at the other fit statistics. Rmsea, root mean square error of approximation, that has error in it, so we want it to be small. It's about 0.08, so it's right on the cut. Nope, my internet's gone again, isn't it? Am I back? It was. Okay, am I back? You came back. Okay, good. I just now can. Okay. Thank you. Yes, squishy being the technical term for that makes me uncomfortable. Uh, because it's like this is my gateway to interpreting my model. And it's just not wrong. Like it's like close to being a problem. Like I'd want to know if there's anything I can do to fix it before I interpret my model. I want it to be really non-significant so I can feel good about that. Rmsea is less than 0.08. Like it's just barely less than 0.08. The other one, CFI, And TLI, these ones are relative to the null model instead. So they're telling you something a little bit different. It's not relative to saturated, it's relative to the worst. And those are nowhere near where they should be. So we want them to be above 0.9 or 0.95, and these are falling short. So on the whole, like this isn't terrible, but it's not good enough yet, would be my assessment. Here are the R squares for my variables. So that column gives you the proportion variance accounted for. As you can imagine, that isn't a thing unless you have multivariate normal conditional distribution. But let's figure out where the problem is. So S-stat residuals here is going to give me the residuals for all of the summaries of these data for the means, their variances, and their covariances. So here's this row that has the means. Do I see anything that looks like a problem in this? No, zeros are good because what I'm looking at is how far off each variable's mean is from the one that is predicted for them. They're all perfect because each variable has its own intercept. Likewise, down here, this covariance matrix is the discrepancy in covariance between what the data say and what your model says. So we want these to all be zeros too, but they're not. And in particular, that one jumps out at me. So we're missing an association there. There is a relationship between mom's education and dad's attitudes that's not being accounted for by the model. That covariance is off. And it's a negative association in this case. There's also these two potentially that are of issue. So this process here is the diagnosis of local fit. Like if your model doesn't fit on the whole, where is the problem? And it looks like we need to add mom's education in as a predictor of dad's attitudes for sure. And for symmetry, I'd probably add it in for kids' attitudes since dad's is already there. And here's the voodoo modification indices. It's telling me the same thing. So this MI column here, that's how much your chi-square would go down for your test of model fit if you added that parameter. And it tells you what the expected parameter would be. So the first one here makes no sense because it's already in the model as a covariance. It wants me to have mom's marital attitudes predict dad's marital attitudes. The second one is the one that I could add and should. That is the slope of mom's education predicting dad's attitudes. So we can add that. And that will be what we do next. And it's going to fix it. I'll spoil the surprise. Okay. We scroll up a little bit, look at the fit. How are we doing? So the new part of this process is really just the fit assessment. Otherwise, it's just a bunch of models run at the same time. And this is why I would suggest in practice with path models, I would generally shoot for a path model that is just identified. Put all the paths in. Then you can't be wrong. So if I had all possible paths, all of these fit statistics would be perfect. And then I could focus on interpreting the paths and seeing which ones were significant and in which direction. And I don't have to worry about getting it wrong. So that is my general recommendation unless the model is just so complicated that that's not a reasonable thing to do, which is not usually the case. All right. Let's see. So do you feel like you could do this in Stata if you had to? Maybe? All right. The next piece of this is M plus, but let me skip through that for just a moment and show you the standard code for the revised model. So I have added in the two slopes that the local fit suggested that I needed. I need to have mom's education predicting dad's attitudes and predicting kids' attitudes. I added kids for symmetry. This model then, I am showing you in Stata how you could do it using mixed as a multivariate model using a stacked data set. So that continues part 1. And here's what it would look like as a path model instead. Relative to what we looked at before, there are 2 new terms in that line. Rather than mom's education just predicting her own attitudes, they're predicting all 3. And survey says, did I have the Stata output in here this time? I don't know that I did. Yeah, I didn't. Well, I'll spoil your surprise. Here's the fit information from M+. Here's our new chi-square test of model fit. I still have 4 degrees of freedom remaining, so it's still over-identified, but now my chi-square is down to 1, which gives me a p-value of 0.9. So really good. Rmsea went from 0.08 down to 0, and CFI went all the way up to 1. So, hooray. Adding in the missing paths fixed it. So I'll show you the M+ code next time, but as part of the results section, here's my path model. Ta-da! So this is what we just estimated. I'm watching Jing do the calculus in her head, tracing all the lines, right? Yes. By convention, when drawing these things, just like you read either top to bottom or left to right, you tend to put your predictors on the left side and the outcomes on the right side. So path models tend to flow. I guess I'm doing it backwards for you guys that way. Or they can go flow top to bottom in terms of like the causal sequence of arrows. If you try to do it another way, you'll confuse people. Another thing that I like to try to do to keep the diagram from looking too hard to understand is use different line types. So like all of the things that are child variables have this type of line. The mom variables had a solid line and the dad variables had a different kind of line. That helps to sort of visually separate it. If I'm giving a talk or something, I would make the lines different colors. So you can talk about like the red lines are the effect of this variable, the blue lines are the effect of that variable, something like that. So you can get creative in how you use these things to convey the model, but this does work really quickly to convey what's going on in something that's very complicated. If I wanted to, I could add the standardized paths, the numbers to these paths, and then I would point out which ones are positive, negative, and so forth. So, all right. Questions before we adjourn? All right, the next time I will show you the M+ code, and then we'll look at example 5A, which is the difference scores. And then we'll be able to do the mediation stuff in our last week of class. All right, so office hours start now. If any of you want to stick around, otherwise, have a good weekend. Take care of yourselves and come back next week. You can't see me, but I'm going to wave. Hang on, start my video so that I can wave too. Bye, guys.